The next application example is slightly more involved. So what we have here is a propped cantilever beam. You have a cantilever end and a roller at the other end, C over here, and in between you have a concentrated load and a uniformly distributed load. Now on an apparent glance, it may seem to you it's a statically indeterminate structure, but your saving grace is this pin. So you have an internal pin which is given over here. So let's just mark that you have a pin, right? So for this particular beam under this loading configuration, we are going to have to draw the shear force diagram and the bending moment diagram. Now before doing that, let us try to mark the reactions that we have over here. At A you will have vertical reaction force RA. Now since A is clamped or fixed, you will have a moment that will develop also. So let me call this M of A, and at C I will have a reaction RC. Right now I marked the reactions and the moments as per my wish. Later the problem will come back and tell me whether I marked it in the right direction or not, right? So this problem will split it in two phases. In the first phase we'll find the reactions. You guys know how to do this already, but just for the sake of clarity, we'll find the reactions first, that is RA, RC and MA, because as you can tell, apparently it seems like you have three unknowns but two equations of equilibrium only. Since your equation of equilibrium along the x direction, it doesn't lead you anywhere. Now after we find the reactions, in the second phase we will draw the shear force and the bending moment diagram. So first let us find the reactions. So to find the reaction, as you can tell that at the pin I'm going to split the beam into the left half and the right side, and I'm going to mark a bx or by over here and equal and opposite b on the other side. So if I have to kind of go ahead and split this beam into two, so let's say these are my two parts. So let me mark the right part over here. So I have in this portion I have RC, and I have the uniformly distributed load of 400 Newton per meter, right? And at this end B over here, where this is my end B, at this B I'm going to simply mark my reaction, say like this, say this is my by, right? So this is the part from B to C. Now similarly from the part from A to B, of course you are going to have the reaction RA over here. We are going to have the MA. We are not going to make use of this, but just to show, just for clarity. And now since I have marked my by as vertically up over here, in the other half I must have my by which is acting vertically down. So this is my by. Right now, from the solving the equilibrium of this particular part over here, we can find out what is going to be RC. How do I do that? Let me take the moments about this particular point B over here. So in this one, if I take the moment about B, what do I get? I will get your RC times this distance. This distance is 2 meters. So here you have, this is given in the problem, 2 meters over here. So RC times 2 will be equal to your 400 times 2, that is the total magnitude of the load, and is acting at the midway, so at 1 meter times 1. Okay. So that should give you your RC as equal to 400 Newton. Right. So now that I know that my that at C the vertical reaction is 400, so this I have come and found out that this is 400 Newton. Right. Then you can solve the equilibrium equation for the entire system. So now you have the system where there are two unknowns and two equations of equilibrium, one Fy equals to 0, and if you take the moment about any point you will get the value of Ma. So I'm not going to go ahead and do that. So what you will get, and try doing this, what you will get eventually is that we have already found out RC over here, and the other values, for example your RA works out as, I have this solved here already, so I'm just going to go ahead and write the expressions that we get over here. So RA is comes out as 1000 Newton, and MA comes out as negative of 2800 Newton meter. So what does that mean? That means that I have marked my this thing in the proper direction, 400 Newton. This is also proper, so this comes out as 1000 Newton. So let me just write it over here. So it comes out as 1000 Newton, and MA, this particular moment, comes out as a negative 2800. So that means ideally the shape should be in the other side, the direction of the arrow should be in the other side. So let me just write it over here. So this comes out as negative 2000 Newton meter, or in other words, if you now, after you calculating, if you want to mark it on the correct side, this M should ideally be acting something like this over here. So this will be a positive 2800, right? So now that we have the reactions which we have calculated, let's move on to the phase 2. In the phase 2, with all the reactions known, now we will find the shear force diagram and the bending moment diagram.